All right, this is going to be our walkthrough for the homework assignment titled Tangent and Secant Line Approximations. So all we're going to be doing here is approximating the value of a function using either a tangent line or a secant line, and then determining whether the function is concave up or concave down to tell us whether or not the approximation we're getting is an underestimate or an overestimate. So in order to use a tangent line to approximate the value of a function, we need to write the equation of the tangent line first. So we want the tangent line to x squared over x minus 1 at x equals 2. So we need the point, which will be f of 2. So we'll find f of 2 first. And so f of 2 should just be 2 squared over 2 minus 1, which is 4. So the point that we're looking at is the point 2 comma 4. And then we need the slope here. And so our slope should come from the derivative of our function. Well, the derivative of our function, the derivative of x squared over x minus 1, we'll find using the quotient rule. Right? So our slope here will be the denominator times the derivative of our numerator minus our numerator times the derivative of our denominator all over the denominator squared. We'll simplify this out a little bit, which will give us 2x squared minus 2x when I distribute the 2x to the x minus 1, and then a minus x squared over x minus 1 squared. And then when we finish simplifying that out, we get x squared minus 2x over x minus 1 squared. And so we're asked to do this at x equals 2. So f prime of 2 will just be whatever we get when we evaluate this at 2. So 2 squared minus 2 times 2 over 2 minus 1 squared. Well, that just comes out to be 0, right? The numerator there is 0, 0 over 1. So we end up with just 0. So our slope is actually 0. Therefore, the tangent line is just a horizontal line. And it should be a horizontal line with the y value that we got at f of 2. So the tangent line is just y equals 4, which tells us that our approximation for f of 2.1 is that it's approximately equal to 4, because that's the only value that our function takes on for any x values. So our approximation is 4, and then we're going to need to use the second derivative to determine what the function is, how the function is behaving there, if it's concave up or concave down. So our first derivative was x squared minus 2x over x minus 1 squared. So in order to find the second derivative, we'll just use the quotient rule to find the derivative of that. So that'll be x minus 1 squared times the derivative of x squared minus 2x, which is 2x minus 2. And then minus x squared minus 2x times the derivative of x minus 1 squared, which is 2 times x minus 1. All over now x minus 1 to the 4th power. And so hopefully we can see right off the bat that I can cancel out an x minus 1 with an x minus 1 with an x minus 1, right? I have to have it in all of the terms, right? So this one's just going to become x minus 1 times 2x minus 2. And this will become minus 2 times x squared minus 2x over x minus 1 to the 3rd power. Now, we can simplify this further if we want, but really what we mostly care about here is just how the function's behaving when x is 2. So I'm just going to evaluate this at x equals 2, which is going to give me first off, it's going to be 1 for x minus 1. And for 2x minus 2, it's going to give me 2. And then it's going to give me a 0 on the back half of this, right? It's going to be 2 times 4 minus 4, which is just 0. Right? And so then on the denominator, we just have 1 to the 3rd power. So it looks like we end up getting 2 here. And we know that 2 is greater than 0, which tells us that this function is concave up. And so when we use a tangent line to estimate a function that's concave up, if you don't remember, I suggest just drawing a quick sketch of a concave up function and then draw a little tangent line next to it. We can see that for any value of our function, if the function is concave up, the tangent line is going to be below the true value of the function. Therefore, this is going to be an underestimate. All right, for our second one here, we're going to use a secant line on the interval from 1 to 3 to approximate the value of 2 for this function. So in order to use a secant line to do the approximation, we need to find the slope through the points at 1 and at 3. So we need to do f of 3 minus f of 1 over 3 minus 1. And so we'll need to find f of 1 and f of 3. F of 1 is going to be 1 minus 3 plus 1, which is just negative 1. And f of 3 is going to be 3 to the 4th, right, which is 81, minus 3 times 9 minus 27. So we have 81 minus 27 plus 1, write that out, which is just 55. So we've got 55 minus negative 1 over 2, which gives us 56 over 2, which is 28. Okay. So our slope that we're using is 28. We can write our tangent line using either of these 2 points, either the point 1, negative 1, or the point 3, 55. I'm going to use 1, negative 1 just because, or not tangent line, sorry, secant line. Using either of those points, I'm going to use 1, negative 1 because, I might as well use the one that's got the smaller values. So our secant line is going to be y minus negative 1, or y plus 1, equals that slope times x minus 1, just leaving it in point slope form. We want to approximate the value of the function at 2, so we'll just plug in 2 to this. So at x equals 2, we have y plus 1 equals 28 times 2 minus 1, or y plus 1 equals 28, or y is approximately equal to 27. And then we're going to need to find whether this is an underestimate or an overestimate, which means we need to find the second derivative so we know if the function is concave up or concave down at that on that interval from 1 to 3. And so if we then go ahead and find our first derivative, we get 4x cubed minus 12x. And our second derivative then, I don't know why I said 12x, 4x cubed minus 6x. 3 times 2 is 6. 4x cubed minus 6x, that'd be much better. And then our second derivative is 12x squared minus 6. And so we just really need to know what's going on at 2, but it's nice to know if there's any changes in the concavity between 1 and 3. So if we do set this equal to 0, we get x squared equals a half. And clearly solving x squared equals a half isn't going to give us any change between 1 and 3. So really we just need to check what's happening at 2. At 2, we have 12 times 2 squared minus 6. And well, that's 4 times 12 is just 48 minus 6 is 42, which is greater than 0. So that tells us that our function is concave up. And if the function is concave up, just sketch a concave up graph and a secant line. You can see that the secant line on the interval in which the function is concave up is going to be an overestimate. It's going to be above the true value of the function. All right, for this one, we're back to a tangent line, which means we need to plug in -3 to the function to find the point, and then we need to evaluate the derivative of our function at -3. So first we'll just plug in -3. We'll find f of -3. Be -3 squared minus 3 times -3 plus 1. So that comes out to just be 19. We have 9 plus 9 plus 1 is 19. And then we want f prime of x. F prime of x is 2x minus 3. And so f prime of -3 will be 2 times -3 minus 3, which is -6 minus 3, or -9. So there's our point and our slope. Our tangent line equation should just be y minus 19 equals -9 times x minus -3, or x plus 3. And we want to approximate the value of our function at negative 2.9. So we'll put in negative 2.9 here for x. Okay. So negative 2.9 plus 3 is just positive 1/10, positive 0.1. When I multiply that by negative 9, I get negative 0.9. And we'll add 19 to that to get y is equal to 18.1. So that's our approximation. And then we need to use the second derivative to determine if it's concave up or concave down. So our first derivative was 2x minus 3. Our second derivative is just going to be 2, no matter what, for any x value. So 2 is greater than 0. Tells me this function is concave up. And again, if the function is concave up and you have a tangent line, that tangent line is going to be an underestimate. And when you're writing these out on the test, I do want you to indicate that it's concave up. And the fact that it's a tangent line on it being concave up is what makes it an underestimate. All right, another secant line one here. So we're going to use a secant line on the interval 0 to 4 to approximate the value of 1.5. So first, we need to find the value of f of 0 and of f of 4 so that we can find the slope of the secant line. So f of 0 is just going to be 1/2. And f of 4, well, f of 4 is going to be 4 plus 1, which is 5, over 4 plus 2, which is 6. So 5/6. So our slope ought to be 5/6 minus 1/2. I'm going to rewrite 1/2 right now as 3/6, just so I have a common denominator there, over 4 minus 0. 5/6 minus 3/6 would be 2/6, right? So we have 2/6 over 4. 2/6 is a third, and a third divided by 4 is a slope of 1/12. So we can use either 0.0 1/2 or 4 5/6 to write our secant line equation. I'm going to use the 0 1/2 because that's just a y-intercept. So I can just say my secant line is y equals my slope 1/12x plus 1/2, right? Y equals mx plus b. Don't need to bother with point slope form this time. And then we want to approximate this at 1.5. Or we're approximating our function at 1.5. So we're going to evaluate this secant line at 1.5. I'm going to rewrite 1.5 as a fraction, just since everything else in here is fraction. And 1.5 is 3/2. And so we end up here with 3 over 24 plus 1/2. Well, 1/2 would be the same as 2 over 24. Right? Sorry, not 2. 12 over 24, which is 15 over 24. So our approximation is 15 over 24. And we're going to need a second derivative here to determine whether this function is concave up or concave down. So first we'll have to take our first derivative, right? So f prime of x we'll find using the quotient rule. So our denominator times the derivative of the numerator, which is just 1, minus the numerator times the derivative of the denominator, which is also just 1, all over x plus 2 squared. So that first derivative just comes out to those x's cancel, right? X minus x, and it's 2 minus 1. So we just have 1 over x plus 2 squared. And then we can find the second derivative here using either the quotient rule or the reciprocal rule. I'm going to use the reciprocal rule. It says that the derivative of a constant over a function is just the opposite of the constant times the derivative of the denominator, which is 2 times x plus 2 to the first power, times the derivative of x plus 2, which is just 1, all over x plus 2 squared, and then squared, so that'd be x plus 2 to the fourth. So really we just have negative 2 over x plus 2 cubed. The only place that this could potentially have a change from concave up to concave down would be when it's undefined, because it's never equal to 0, which would be at negative 2. Negative 2 is clearly not on our interval, so we're just going to evaluate this at 1.5 here, right, or at 3/2. And I think we can see that if I put in we'll put in x equals 1.5 here. If I put in something like 1.5, that denominator is clearly going to be positive, so I have negative 2 divided by a positive, which is obviously going to be less than 0. It doesn't really matter what the value is. It is less than 0, which tells us that the function is concave down. And when you have a function that's concave down and you've used a secant line to approximate the true value, you can see that the true value of the function is above the secant line's approximation, so we've got an underestimate. All right, back to another tangent line one here. This time we're going to approximate the value of 0.9 using the tangent line at x equals 1. So first we need to figure out what is f of 1, so we have a point to use. 2 times 1 minus the natural log of 1. We should know that the natural log of 1 is 0, so this is just 2. So the point we're looking at here is the point 1, 2. Then we need the derivative. F prime of x is going to be 2 minus 1 over x, because that's the derivative of 2x minus ln x. If we evaluate that at 1, we get 2 minus 1 over 1. We get 1. So we have a slope of 1. And the point we're looking at is the point 1, 2. So our tangent line is y minus 2 equals 1 times x minus 1. We're going to approximate this, or we're going to use this tangent line to approximate the function at x equals 0.9. So we'll plug in 0.9 for our y value. We got y minus 2 equals, the 1 is unnecessary, so 0.9 minus 1. Well, y minus 2 then is equal to negative 0.1, or when I add the 2, y is equal to 1.9. And now we're going to need a second derivative to determine if this is concave up or concave down. So our second derivative, we'll find the derivative of the 2. That's just a constant, so it's 0. So really we're just looking for the derivative of negative 1 over x, or x to the negative x to the negative 1, which would be positive 1 over x squared, or positive 1x to the negative 2. So the only place where this would change from concave up to concave down potentially would be at x equals 0, where it's undefined because it's never equal to 0. And that's not between 1 and 0.9, so we don't need to worry about that. So we'll just evaluate this at 1, which gives us 1 over 1, which is a positive value. Since we have a positive value here, and the function means the function is concave up, and a tangent line will be an underestimate. So we'll note that this is making it concave up, and that means it's an underestimate. All right, and here's our last one. We're going to use a secant line on the interval from negative 1 to 1 to approximate the value of f of 0.2 for x cubed plus the inverse sine of x. So first off, we need to evaluate f of 1 and f of negative 1. So f of 1 is going to be 1 plus the inverse sine of 1. And f of negative 1 is going to be negative 1 plus the inverse sine of negative 1. And of course, when we evaluate inverse sine, we have to remember that there are an infinite number of values where when you take the sine, you get 1. But inverse sine only operates from negative pi over 2 to pi over 2. The output, the range of inverse sine is only from negative pi over 2 to pi over 2. So the only value on that interval that we get for when we take the sine of something to get 1 is pi over 2. So we get 1 plus pi over 2 here. And likewise, for inverse sine of negative 1, it's still got to be between negative pi over 2 and pi over 2. That's going to be at negative pi over 2. So we have negative 1 minus pi over 2. So those are our two values. We'll use those to find our slope. So we'll do f of 1, 1 plus pi over 2, minus negative 1 minus pi over 2, f of 1 minus f of negative 1 over 1 minus negative 1. That should give us our slope. So in the numerator there, the 1 minus the negative 1 is 2, and pi over 2 minus negative pi over 2 would be just pi. So we have 2 plus pi over 2. So our slope is going to be 2 plus pi divided by 2. Right? And so we can pick either point. I guess I'll pick the point 1 and 1 plus pi over 2 to write my secant line equation. So my secant line is going to be 1 minus 1 plus pi over 2 is equal to 2 plus pi over 2 times x minus 1. And now we'll just need to evaluate this at 0.2. So that'll give us y minus 1 minus pi over 2, when I distribute that out, is equal to, I'm going to rewrite the 2 plus pi over 2 as just 1 plus pi over 2 for now. And then I'm going to multiply that by my 0.2 minus 0.1, or sorry, minus 1. So we've now got y minus 1 minus pi over 2 is equal to, that becomes a negative 0.8, right? So when I distribute the negative 0.8 here to the 1, I get negative 0.8. And when I distribute it to the pi over 2, I get negative 0.8 pi over 2. And so we should be able to kind of sort of combine some stuff together here. If I add over the 1, right, I'm going to end up with negative 0.8 plus 1, which is 0.2. And 0.2 is, well, 1/5. Right? So we get 1/5. And then if I add pi over 2 to negative 0.8 pi over 2, that should be, if I rewrite this, okay, I'm going to rewrite, I guess we'll rewrite that 0.8 pi over 2. That's the same as 8 pi over 20, right? And 8 pi over 20 would be the same as 2 pi over 5. So I've really got 2 pi over 5 plus pi over 2. Or really, I guess we should rewrite that as 4 pi over 10. And then we're going to add to that 4 pi over 10 negative 4 pi over 10, right? Because those are all negatives. We're going to add this over, which is 5 pi over 10. So negative 4 pi over 10 plus 5 pi over 10 is going to be pi over 10. Or if you prefer to get a common denominator, you can call it 2 plus pi over 10. That'd be fine as well. Any of those are fine. Or you can write it as 0.2 plus pi over 10. Really, any of those values are fine. So there's our approximation. And now we just need to find a second derivative to determine if the function is concave up or concave down. So our function was just x cubed plus the inverse sine of x. So the first derivative should be really easy. F prime should just be 3x squared plus the derivative of inverse sine, which is 1 over root 1 minus x squared. And then to find our second derivative, we'll just take the derivative again using the power rule for the 3x squared. That's just 6x. And then root 1 minus x squared in the denominator is like 1 minus x squared to the negative 1/2. So I can just use the chain rule on that, right? U to the negative 1/2. So it becomes minus 1/2 of 1 minus x squared to the negative 3/2. And then I have to multiply that by the derivative of 1 minus x squared, which is negative 2x. And so when I simplify this out a bit here, I get 6x. The negative 1/2 with the negative 2x should cancel out. We're just going to end up with a plus x over 1 minus x squared to the 3/2. And if we evaluate this when x is equal to 0.2, we end up with 1.2 plus 0.2 over 1 minus 0.2 squared to the 3/2. Well, 1 minus 0.2 squared, right, is going to be a positive number. And if I take a positive number, I can square root it with the 3/2 and then cube it, and it'll still be positive. And then if I do 0.2 divided by a positive, that's all positive. And if I take it and add it to another 1.2, that's still positive. So this is greater than 0, which tells me that the function is concave up. If the function is concave up, then a secant line should be an overestimate. And that's the end of our walkthrough here. So the basic idea is if it's a tangent line, find the point, find the slope, write the tangent line equation. And then if it's a secant line, find the slope by finding the slope between the 2 points at the ends of your interval. And then write your equation using that slope in one of the points. And you'll always need a second derivative of the function in order to determine if it's an under or an overestimate. Just sketch the little picture, whether it's concave up or concave down, to determine for a secant or tangent line whether it's under or over if you don't have it memorized.